$003, a price tag you wouldn't expect for this level of innovation. Tesla's Model 2 has just turned the entire industry on its head. And it's not just because of its affordability. This is some crazy, crazy technology we got in this car. Crazy technology. Crazy, crazy. So different than what was previously announced. And yes, are you ready for what's coming next? Because the recently leaked test details have revealed an experiment of 3 new features on this model. A nearly indestructible polycarbonate windscreen. A thermal loop frame that transforms cabin comfort. And a weight-adaptive floor plate that adjusts performance and safety on the fly. Together, they've shattered expectations and set off a wave that's rattling the U.S. automotive world. Are you tired of the same recycled automotive news? If yes, then stay here, because we added new details, updated insights, and fresh analysis that you won't want to miss. And let's help this channel push forward to 245,999 subscribers by just subscribing. Let's move in. How does the polycarbonate windscreen introduce a structural level upgrade that Americans never expected in a $10,577 EV? Drivers in California, Texas, Florida, and New York deal with impacts, debris, and extreme temperature swings every single day. Traditional laminated windshields reach their limits fast, showing microfractures and cracking under stress. Tesla Model 2 introduces something entirely unexpected: a polycarbonate windscreen that operates on a completely different structural level. So, how does a polycarbonate windscreen, engineered with multi-layer compression and thermal coating change, impact durability, temperature performance, and long-term cost for a $10,577 EV? Tesla swapped out conventional glass for a 0.27 to 0.33 inch multi-layer polycarbonate laminate, 3 distinct layers working as one system. A flexible outer energy distribution layer that spreads impact force across the surface. A UV-stabilized structural core that maintains rigidity without brittleness. And a heat-reflective inner coat that cuts cabin thermal load before your AC even kicks in. This material deflects under stress instead of shattering and works with the driver, not against them. Here's the problem nobody talks about. Typical laminated glass develops microfractures after just 80 to 120 heat-cold cycles per year. That's one summer-winter cycle in most American climates. Polycarbonate maintains structural integrity across over 500 cycles, solving sun-induced expansion in Texas and Florida, freeze-thaw contraction in New York, and high-debris environments across California's Interstate 5 corridor. When gravel hits glass at 55 miles per hour, it cracks. When it hits polycarbonate's flex response surface, it bounces off. Different outcome, different material category. The technical performance is brutal in its efficiency. Impact resistance increased by 160 times compared to tempered glass, absorbing 150 to 180 feet L, be a force without failure. Flex deflection tolerance runs 0.08 to 0.09 inches under high-speed impact, which is enough movement to dissipate energy without compromising visibility or seal integrity. Weight drops by 6 to 8 pounds, lowering front-end inertia and delivering a 2.9% urban efficiency gain that adds up over 12,000 miles annually. Solar load reduction cuts cabin temperatures by 14 degrees Fahrenheit to 20 degrees Fahrenheit, which slashes HVAC draw by 9% to 12% correspondingly. That's not comfort engineering. That's thermal management baked into the structure. Controlled debris testing demonstrates a dramatic improvement, showing that at 55 miles per hour, the polycarbonate windscreen avoids cracking in 87% to 92% of cases, far outperforming traditional laminated glass. Long-term sun exposure testing in southern climates slowed UV haze formation by 30% versus uncoated polycarbonate. Freeze-thaw cycling performed over 1,000 iterations showed 0-layer delamination. These aren't lab fantasies. These are certification-grade results. What sent shockwaves through the U.S. market is this. Over the past 12 months, the insurance industry recorded more than 3.8 million glass-related claims. with each laminated windshield replacement costing between $350 and $480. The composite windscreen removes up to 70% to 80% of common brake scenarios, disrupting actuarial models nationwide. Fleet operators in California and Florida reported that polycarbonate panels cut downtime from minor road debris incidents by roughly 40%, an outcome never associated with low-cost EVs. Heat-resistant performance also lowered cabin temperatures by 14 degrees Fahrenheit to 20 degrees Fahrenheit, surprising HVAC analysts who previously assumed such gains only existed in luxury EVs above. Sen 1 material. Engineers highlighted that polycarbonate of this thickness and clarity has never been mass manufactured into a sub-1 vehicle, let alone one under $11,000, causing unexpected shifts in supplier demand forecasts. Senior advocacy groups in Texas and New York identified the reduced replacement costs as a key affordability milestone, pushing the Model 2 into the attention of state-level transportation committees. Unusual reaction for an entry-level EV? Internal insurance. Projections suggest the Model 2's windscreen design may cut lightweight impact claims by 25% to 30% nationwide. That's category disruption. For seniors managing fixed incomes, this eliminates recurring $480 windshield replacement costs that drain budgets every 18 to 24 months. Reduced heat load benefits respiratory comfort for older passengers and lowers operational costs per drive. It's the type of upgrade that reduces stress, lowers maintenance costs, and keeps daily driving consistent, especially for older drivers managing budget concerns. And here's the big question nobody in the industry wants to answer. If polycarbonate can handle 500 temperature cycles and deflect 55 miles per hour gravel impacts in a $10,577 EV, why is the rest of the industry still using glass that cracks after 80 cycles? Let's drop polycarbonate in the comments if you're done paying for windshields that weren't engineered to last. But material innovation on the windscreen is just surface-level disruption. Tesla embedded thermal management directly into the vehicle's structural skeleton, with continuous heat regulation that doesn't add cost or weight, and this innovation caught engineers completely off guard because nobody expected this level of sophistication at this price. Heat and battery degradation are the two biggest performance killers for affordable electric vehicles. Most low-cost EVs struggle with uneven cabin temperatures, HVAC overuse, and faster battery wear. But the Tesla Model 2 flips that dynamic completely with a chassis-level cooling structure. How does embedding coolant channels inside the pillars, rocker beams, and subfloor crossmembers stabilize temperature better than traditional radiators on vehicles priced far higher? Tesla machined coolant microchannels directly into the structural frame during extrusion. The pillars that hold your windshield, the rocker beams under your doors, the cross members beneath the floor, they're all circulating coolant. Now a single low-power pump sustains 1.9 to 2.4 liters per minute flow, providing distributed heat dissipation across massive surface areas that were previously just dead weight. This isn't adding cooling. It's turning the skeleton of the car into a passive radiator. The performance gap is immediate. Heat rejection improved by 22% to 28% versus conventional isolated radiator systems. Cabin cool down from 120 degrees Fahrenheit to 76 degrees Fahrenheit. Shortened by 55 seconds critical when you're sitting in a Texas parking lot at 2 p.m. winter warm-up. Energy use lowered by 9% to 12%, which matters when New York's cold drains your battery before you leave the driveway. Battery thermal variants stabilize within 3 degrees Fahrenheit, improving long-term cell health by 7% to 11%. That translates into years of additional battery life before capacity drops below usable thresholds. Here's how the system works. A pillar and rocker beams act as passive radiators, rejecting heat into airflow without fans or pumps working harder. Microchannel distribution prevents hotspot formation. No single area of the battery pack cooks while another stays cool. Cabin sensors modulate coolant temperature rather than forcing high-power HVAC cycles that burn range. The car regulates itself structurally, not electronically, In terms of cost and weight reduction, Tesla removed one secondary radiator and one coolant reservoir. Net weight savings are 11 to 14 pounds. Material cost is nearly unchanged because extrusion-based. Manufacturing of channels adds almost zero expense to frame production. You're getting thermal stability that luxury EVs achieve with $1,800 active. Radiator systems except Tesla achieves equivalent stability through frame geometry, not expensive hardware. In real-life conditions, lower HVAC load translates into lower electricity costs per month. Seniors on fixed incomes notice every dollar saved. Reduced heat shock improves comfort for older drivers with heat sensitivity. Can't tolerate cabin swings between 90 degrees Fahrenheit and 70 degrees Fahrenheit every 10 minutes. Enhanced battery lifespan means fewer expensive replacements across 8 to 12 years. Eliminating the single biggest ownership fear for budget EV buyers, the U.S. market was shocked when distributed heat rejection, previously seen only in aerospace and refrigerated transport, appeared in a $10,577. EV engineers across the industry openly admitted they never expected frame integrated cooling at this price. Battery aging projections fell 11%, reshaping cost of ownership. Models for older drivers and young families alike. Climate labs in Arizona and Florida recorded 12% lower HVAC loads at identical ambient temperatures, confirming that the Thermaloop frame isn't a theoretical improvement, it's a real-world efficiency multiplier. Energy analysts found that over 1 year of mixed driving, a Model 2 saved the average driver between $110 and $185 in electricity costs. So,